Hello everybody, welcome into another lesson. So today we are going to talk about direct variation. So what is direct variation? Well, you may see a sentence like y varies directly as x when y equals a and x equals b. So that a is some arbitrary constant and so is b. The general form of a direct variation equation is y equals k, which k is the constant of variation, times x. So y equals x times some constant of variation. Now, in this case, you're given some arbitrary values for a and b. So the first thing you want to do then is solve for your constant of variation. Of course, you would just solve for k, which would turn into the value of y over x. In this case would be a over b. And then to find your equation of direct variation, you set y equal to the value of your constant of variation times x. So y would equal a over b times x. And then you also may be asked to find the value of y when x equals a certain value right after that. But we're going to do some problems here. And then I'll show you how it works here. So in this case, we want to solve for x equals, sorry, that wasn't right. Y is 7, x equals 2. Okay, so y varies directly as x when y equals 7 and x equals 2. So, of course, the first thing we want to do is set up your general equation, y equals k times x. Well, we want to solve for that constant of variation, so all you're going to do is plug in your x and y values into this and solve for k. So 7 we would plug in for y, you would have k times your x value of 2, and to solve for k, just divide both sides by 2, you would get that k equals 7 halves. So your constant of variation is going to be 7 halves. Which then, now that you know what the constant of variation is, you'll set y equal to that constant of variation, which is 7 halves times x. So there's one facet. We found the equation for direct variation. We also have another facet of this, and then, which I should have listed up here, find y when x equals 8. So now we have a hope of doing that since we solve for our equation of variation. If you want to find y when x equals 8, just take y, set that equal to your constant of variation times your x value of 8. Well, 7 halves times 8, that would end up being 28. So y would equal 28 when x equals 8. So that's how those are going to work, and I'll leave up the equation of direct variation. But let's put in some different values here. In this particular case, we have that y is 15, and then x equals -6. So y varies directly as x when y equals 15 and x equals -6. So first, let's set up our equation of direct variation, y equals kx. Let's solve for the constant of variation. So y is 15, so 15 would equal k times your value of x being -6. Now divide both sides by -6, you'll get the answer for k. K would equal 15 divided by -6, which would give you -5/2. So your constant of variation is -5/2. Now set up your equation to be y equals that constant of variation of -5/2 times x. So there's the equation of direct variation, y equals -5/2 times x. Now the other facet of this is solve for y when x equals 8. So we'll set y equal to -5/2 times the x value of 8, which would end up giving you that y equals -20. So when x equals 8, y would equal -20. And there is another type of variation that we'll discuss later on in the course. It's called inverse variation. And then there's joint variation, which combines elements of both direct and inverse variation all at once. But those will be later in the course. Okay. This time we have y equals 9, x equals -3. So y varies directly as x when y equals 9 and x equals -3. So here's the standard form of the equation for direct variation, y equals kx. Go ahead and solve for that constant of direct variation. So y is 9, set that equal to k times your x value of -3. To solve for k, divide both sides by -3. 9 divided by -3 is -3. So your constant of variation is -3. So now put that into your equation. Y would equal -3x. So your equation of direct variation would be y equals -3x. Now, the other side of this is we need to find y when x equals 8. So take y equals -3 times that x value of 8. You would get that y equals -24 when x equals 8. So yes, y would equal -24 at that point. All right. We have, let's see, y is 4, x is 24. So y varies directly as x when y equals 4 and x equals 24. So let's go ahead again, solve for your constant of variation. So if y is 4, that's going to equal your constant of variation, k, times your x value of 24. Now to find k, your constant of variation, divide both sides by 24. Well, 4/24 turns into 1/6. So your constant of variation is 1/6. Now, just plug that constant into your equation, you would get y equals 1/6 x. That would be your equation of direct variation, would be y equals 1/6 x. Now, we need to find y when x equals 8. So y would equal 1/6 times 8. Well, what is 8/6? Divide both numerator and denominator by 2, you would get 4/3. So you would get a y value of 4/3 whenever x equals 8. Two more of these, then we're going to do a few sets of data and determine if they represent direct variation or not. All right, what do we got here? So let's see, y is 1/2 and x is 1. All right, so y varies directly as x when y equals 1/2 and x equals 1. So let's go ahead and set up let's set out to find our constant of variation. So we'll take that 1/2, put it in for y, set that equal to k times our x value of 1. Well, k times 1 is just k, so your constant of variation would in fact be 1/2. So that was easy. Constant of variation is 1/2. Now you just take y, set that equal to your constant of variation of 1/2 times x. So your equation for direct variation in this case is y equals 1/2 x. Now we need to evaluate we need to find y when x equals 8. So take y, set that equal to your 1/2 times your x value of 8. Well, half of 8 is 4. So you would get a y value of 4 when x equals 8. One more of this, and then we're going to do a set of data. We're going to do a few sets of data here to determine if it represents direct variation. All right. Let's see, y is 1.6, x is 0.8. All right. So y varies directly as x when y equals 1.6 and x equals 0.8. Well, let's find our constant of variation, k. So put in 1.6 for y. Set that equal to k times your x value of 0.8. Divide both sides by 0.8, you'll get your value of k, which would be 2. So your constant of variation is 2. Now just put that into the equation. Y would equal 2x. So the equation of direct variation is y equals 2x. Now we just got to find y when x equals 8. So y would equal 2 times 8, which would give you a value of y being 16. So when x equals 8, y would be 16. So that's how you solve for the constant of direct variation, how to find the equation of direct variation, and then find a value whenever you know the equation of direct variation. Pretty simple, right? It's really quite simple. You can also, we're not going to do it today because we're only doing linears, but you can have direct variation with quadratic variables, with cubic variables, or other types. That's not the only way you can have direct variation, but I think I'm going to call this lesson linear direct variation to specify. All right. So we're going to do a few sets of data here. We're going to determine, do they represent direct variation? Well, let's come up with those sets of data, shall we? Alright, so we are given some x and y values in this set of data. We need to determine, does this set of data represent direct variation or not? How are we going to determine that? Well, take each piece at a time. Do yourself a favor, set up an equation of direct variation, right? We know that to be, in general, the equation of direct variation is y equals kx, right? If this set is truly direct variation, that means for every x value to y, every single one should all have the same constant of variation. If even one of them doesn't have the same constant of variation, then this set does not represent direct variation. They all must have the same constant of variation in order for it to be direct variation. So let's start with 2 and 1, right? So y equals 1, and then you have the k times your x value of 2, which would give you a constant of variation equaling 1/2. All right. Now, how about 4 and 2? So y equals 2, then you have k times your x value of 4. Well, k would equal 2/4, which means k also equals 1/2. So far, so good. With these two, it looks like it. Now, how about 6 and 3? So y equals 3. 3 equals k times your x value of 6. Well, 3/6 is 1/2. K equals 1/2. So far, so good. All right, how about 8 and 4? So 4 for y equals k times your x value of 8. Well, 4/8 is also 1/2. You got a constant of variation of 1/2. And then last but not least, we have 10 and 5. So 5 would equal k times your x value of 10. Well, 5/10 is definitely 1/2. You have a constant of variation of 1/2. And every single x to y value has a constant of variation of 1/2. So the answer is yes. This set of data does represent direct variation since every x to y value has the same constant of variation. I'm going to leave the general form of the equation up to make life easier. We'll do another set of data here. All right. What about okay, so we have another set of data here. We need to determine, is this set of data, does it represent direct variation? Well, again, so take your first y value of 5, set that equal to k times your x value of 1, which would give you a constant of variation of 5. Well, that's the beginning. Now let's deal with 2 and 4. So y is 4, so 4 would equal that constant of variation k times your x value of 2. Well, in this case, you get a constant of variation of 2. Right away, we have two different constants of variation, so no. We can stop there. We don't even have to care about the other numbers. You've already found something different. So no, this does not represent direct variation, because on the second one you have a different constant of variation. And if you find a different constant of variation, immediately you can stop. You don't even got to go through all the other ones. It saves you a lot of time. Do 2 more of these, then we're done with the lesson. This isn't a super long lesson today. The book had me teaching it in yesterday's lesson, but I thought it should be its own lesson. Alright. What do we got here? 3, -3. 6, -6, 9, -9, 12, -12, 15, -15. Alright, so is this set of data considered a direct variation? So find your first constant of variation. So -3 would go in for y, set that equal to your k times your x value of +3, which would give you a constant of variation of -1. Alright, that's your starter. Now do the same with the y value of -6, set that equal to k times your x value of 6. In this case, you also get the constant of variation as -1. So far, so good. Now take your y value of -9, set that equal to your constant of variation times the x value of +9. Well, you get a constant of variation also of -1. Now how about 12 and -12? So put in -12 for y, set that equal to k times your x value of 12. What do you know? You get a constant of variation of -1. And then put in -15 for y, set that equal to k times your x value of 15. You get a constant of variation of -1. And they all have the exact same constant of variation of -1. So since they're all the same, yes, this set of data does represent direct variation. So yes, this is direct variation based on this set here. I got one more problem, then we're done. All right, last one. Alright, so is this set of data considered a direct variation? Well, let's find out. So take your y value of 10, set that equal to k times your x value of -5, which would give you your constant of variation being -2. So that's just the beginning. Now do the same when y equals 8, set that equal to k times your x value of -4. Well, what do you know? You get a constant of variation also of -2. Alright, so put in 6 for y, set that equal to k times your x value of -3. Well, you get the constant of variation is also -2. Now put in 4 for y, set that equal to your x value of -2 times k. Well, you get your constant of variation being -2. And then put in 2 for y, set that equal to your constant of variation, k, times -1. Well, what do you know? You get a constant of variation of -2. So these all have the same constant of variation, being -2, so yes, this set of data does in fact represent direct variation. So that's it for the direct variation of linear equations. Next lesson, we are going to actually graph linear inequalities. We are going to graph them in the coordinate plane, which will be a fun lesson. So I hope everybody has a great night. Take care.